So thanks very much, everybody, for having me back to Flatiron. It's been a while. So as Dan mentioned, I was a CCQ postdoc from 2018 to 2020. So probably a lot of the people who are postdocs here didn't know me, but it's great to see that there's still so many people working on scientific software here. So as was mentioned, I currently work at Amazon on our service for quantum computing called Bracket. So I work in sort of like research scientist role, but in industry. And my talk today is going to be about kind of the differences and maybe some commonalities I've noticed between the software cultures in academia and industry, maybe things we can learn from one another. And also just if you're interested in pursuing a career in industry, some software development skills that might be useful to do that. So I'll try and keep the slides relatively short since I think we're a few minutes behind schedule. And hopefully we'll be able to have a little bit of a discussion at the end. Okay. So I often think of the sort of two software communities I've been a part of, both in academia and industry, as having a common origin, but they have different mindsets and different tools. So I'm not a biologist, apologies to all the biologists here, but you can kind of think of the way these communities look and think and act as basically rational responses to the incentives they face every day. And although they have a common origin, the way they express sort of the things that they need to do are different because of these incentives that they face. But I still think there's a lot that we can learn from one another, as I'll discuss kind of as we go through. And I think actually one of the biggest differences, and this really informs a lot of the different ways we think about sort of how we're developing and what our workday even looks like, is who the sort of target user we think about, or maybe don't even think about, but kind of just like live through our day imagining we'll use our software is. Certainly in academia, I think we often focus the software we're developing on either people who are already other academics, so that could be like a PI or group leader, or maybe minimum like a trainee, right? Like an advanced undergrad or a grad student from another field who maybe doesn't have our specific domain expertise, but they already know how to write software of some kind, and they probably took like a bunch of undergrad linear algebra or calculus courses even. There's other groups that we also often end up showing our code to, especially nowadays when journals are asking to see code for a publication that's in some sense numerical. Journal reviewers will see our code, but again, those people are usually domain experts. And the other group that's becoming, I think, more common is funding agencies. So probably as many of the folks in this room know, for a long time, it was very hard to get funding to write open source scientific software. Thankfully, that's changing. But now, of course, if you want to write a grant to say like, hey, I have this really cool scientific software, I want to keep developing it with the help of my group or grad students, or hire a full-time software developer, often, of course, they're going to want to see the code. And I think there's also kind of an important distinction that I'll return to in this talk about sort of two, and again, this is like kind of a rough grouping, two sort of groups of software that we write. There's sort of prototypes, and then longer term, larger libraries. So a good example would be like Rosetta or Masala is obviously a library, right? It's like an ongoing project that many people have maintained over many years. But then on top of that, people build prototypes, and that prototype could be like a specific piece of code that they used for a paper or a grant application. And we'll discuss kind of how these change our approach, both in and out of academia. So when we think about prototypes, I would say like usually the main developer on these things is usually like one or two people. Often it's a more junior member of the team. So that could be like a grad student, a postdoc, or again, an undergrad. That person may not be part of the group anymore. So you may often find that there's some repo that has the code for a paper, and the last commit was like 5 years ago. And you want to take that repo and either integrate it into the main library, or you want to run it just to see like, can I replicate this result? But unfortunately, in that interim 5-year period, all of the dependent libraries have changed. They ran this using perhaps an older version of Python that your OS doesn't support. And so it can often be like a large part of the project is just getting the code in this repo to run at all. Often the documentation such that it exists is in the README. Maybe there's some inline documentation, or the documentation that exists is literally just the paper. And there's often not any continuous integration testing. So there's like no GitHub action to test, because, you know, there's just like this code that existed and you can clone the repo and do whatever you want with it. And so to me, this is often like the analogy I draw to myself is like these medieval manuscripts where like this is written in English, and if you probably sat down for a while, you could kind of figure out what it says, especially if you're an English speaker. But it's not so easy to do. Now, when they, you know, whoever wrote this down, they had no problem reading what was written there. But the passage of time and the fact that this was, you know, this specific document wasn't continually updated makes it harder for us now to do that. And of course, if you take like a middle school English class nowadays, you'll see a version of Chaucer that has been updated continuously over time, where they both, you know, they make the writing a little easier to read, and often will also give you a sort of modernized text next to it, because the English language itself has changed over time too. And so people do that because there's an incentive to keep reading Chaucer. So what is an incentive for us in the software community to keep these prototypes current? Because often the only artifact that like really explains how an algorithm works or how it was run is in some GitHub repo with a last commit from like X years ago. And the fact is, you know, people don't keep these current because there's not really an incentive to do it. People are, you know, even scientific software developers are rational people who occasionally respond to positive rewards and negative punishments. So can we find a way to keep encouraging people to maintain these things, or have like a central group that does something like that? I think it's something that's worth considering, because it's, of course, very frustrating if you're trying to replicate something like that. And then, as of course many of us know, there's also these sort of bigger projects that we might call like software libraries or software toolkits. These are, as many of us know, often developed by either a single PI or maybe a collaboration. What I've often observed, at least in like the quantum community, is that you often end up in a situation where there's competing tribes. So you have like one PI and their collaborators, and they're all working on one library, and then another PI who like maybe interpersonally doesn't get along with people in that first one, and so they have their own software library that has very similar goals, but the interface is different. Again, just to keep kind of going with the medieval theme, to me, this is also like very similar to the situation we had in medieval Europe, where you had like these trade leagues that had exclusive contracts to trade with other cities, and they didn't necessarily like people who weren't, you know, you weren't allowed to trade in some of these cities if you weren't part of the Hanseatic League. And people within the league didn't necessarily get along all the time, but they were in kind of a consortium that for them worked great. But the system didn't survive for a variety of reasons. And luckily now we're also starting to see in the academic software world, like more funding for head-to-head comparisons of these kind of competing software consortia, right? Like if we run 5 packages that purport to do DFT, which one is most accurate for this use case? Or if we want to try and solve, for example, the many electron problem, can we try all of the existing software toolkits? First of all, see if they're even capable of solving this. And then second, can we compare the performance and accuracy? And again, this is something that, of course, if there's no incentive to do it, people won't, because they generally respond to incentives. So this is also, I think, an aspect that in the academic community, we can work together to try and incentivize having an honest comparison of these things, especially because, going back to the prototype example, when someone's thinking, you know, okay, there's 5 algorithms that people have developed to try and solve, let's say, this measurement problem in quantum mechanics, but I don't know which one I should devote energy to integrating into my bigger software library. All of the repos are out of date, and I don't have time necessarily to get them updated and then do the benchmarking. And even if I do, that's not publishable. So I guess we're just going to keep having all of these algorithms running around, and nobody will have any particular clarity about which one is best. One thing that is nice about software libraries, again, now that people have kind of maybe realize that there are rewards for doing this, is that they have both sort of inline in the code and then generated documentation, including tutorials. One thing that also I think is quite frustrating about this is that many of these tutorials are really good, but they're not publicly available because they were at a summer school, let's say. And so you go on the PI's GitHub and you see like, 5 repos down, like 2014 Trieste summer school. And then you go look in the repo, and actually there's a lot of great tutorials in there. But those were never integrated into the main library. And that can be frustrating for us. So I think there's also a big opportunity here to find a way to reward people for making that kind of material integrated into the main library. And another thing, again, that has been improving over time, especially because there's more, I think, of an insistence on it from funding agencies, is using things like continuous integration testing, especially on multiple operating systems, different versions of languages, to make sure that you can actually use these software libraries on something besides the perhaps somewhat bespoke system they were developed on. Okay. And so as a scientist who's now working in industry, our target user is often quite different. So we're often interacting with users who are totally unfamiliar with our domain, right? Like we may have somebody coming to talk to us who's, let's say, like an expert in AI or machine learning, but they don't know anything about quantum mechanics. And so you have to find some way to write the software that they can interact with it without first having to get a PhD in quantum physics. And of course, if you've spent, as many of us have, like 15 years marinating your brain in the quantum mechanical jargon, it can be hard to figure out what is difficult for external people who don't know a lot about whatever your specific domain area is. It's very easy to forget when this material was hard and what is or is not intuitive for other users. A good example for me, especially because I do a lot of quantum chemistry now, is for folks who've been immersed in the chemistry or physics community, it's totally natural for us to talk about like a Hartree-Fock ansatz, but 90% of people coming to quantum chemistry have never heard that term. And if you start trying to explain it to them, you say like, yeah, so you draw like a Slater determinant. They're like, no, stop, what's a Slater determinant? And it's not that they are not technical people or that they're not intelligent. It's just we working in our domain expertise communities are so immersed in it's kind of a body of knowledge that we don't even realize that we're living in, that even when we're developing simple prototypes, it can be very difficult to kind of reach the audience where we want to. And then we also have other communities of external users who would be experts. So that could be somebody like at a startup who wants to use your technology to, build their startup's technology or something like that, or an external academic who wants to run something that you provide. And then we also target users who are internal software developers who are going to take something that we sort of show to them as like, this is what's possible. And then they have to take that and write code to make it perhaps like a little bit more maintainable and reliable, which we'll also discuss a little bit further, partly because they're the ones who are going to have to deal with it when it breaks. And then finally, this is actually pretty similar to the funding agency's example for academics, but internally in a team that we work in, we have folks like in management who are making decisions about, okay, we have, let's say, like 30 people on the team and we have 10 projects we could do. How are we going to divide up the headcount among those projects? And one way you can justify doing that, of course, is by developing prototypes, showing them what's possible, and then arguing like why we should do this. But you then have to be able to communicate with that prototype why this matters and come up with a reasonable estimate of how much it's going to cost to do. Cool. So when I transitioned into a more industry-focused role, there were some things that were like a very large surprise to me, and some things, I guess, that were maybe less of a surprise. One aspect I think that we don't discuss a lot in academia is, in general, what you might call like compliance, both with like open source licensing, security compliance, dealing with stuff like fraud. And I think for many people in academia, especially academic software developers, we generally don't have to worry about this stuff. If there's anybody here from SCC, maybe they have a different perspective on how much you have to worry about like things like your equivalent of fraud or security vulnerabilities. We also have to work very carefully to make sure we're not breaking things for users who are relying, for example, on a specific Python version. Again, I don't want to generalize too much about the academic community, but I think in academia, people are a little bit more willing to tell folks like, this Python version you're using is 6 years old. You need to just upgrade if you want to use this version of the software, sorry. But in industry, that's often not possible because software stack that an external customer is using is reliant on like Python 3.6, and it's going to cost them some very large amount of money to switch, so they're not going to do it. And we have to make sure that we can support however many versions of Python, let's say, and it's a very big process to go through to drop it. And we also have to worry a lot about stuff. For example, like if an upstream dependency gets compromised, what are we going to do? How are we going to detect that happening? This is often, at least again, my personal experience, not something we worried about too much when developing academic code. But in an industrial environment where you're asking people to run your stuff on compute hardware they're paying for from you, this can be a really big risk. And we need to just make sure we're accounting for stuff like that. And I think another aspect that was very different for me was sort of the whole building and testing code process is very different. Often in an industrial environment, you want to have sort of a hostless or like machine independent way to build and test the code. So you just upload the code effectively to their equivalent of GitHub, and it runs a bunch of builds and tests on different machine images, different versions of the language. And you have to make sure that nothing in that process is going to break for any of the steps in the pipeline. And once the build is complete, then it'll start rolling forward to different environments. So like a very restricted environment that not many people can see, and then gradually to more and more users. And you need to have a way to detect if things start to break for them, versus just telling people like, sorry, this doesn't work on Mac OS. Either install a virtual machine or just use Linux FAM. Again, not everybody in the academic software world is like this, but I think it's much more common to tell people like, sorry, this software just doesn't work on Mac. And that's how it is. So when we're developing prototypes in industry, often our target isn't so much to have like a publication necessarily, or to argue to a funding agency like NSF or DOE that they should keep funding our library. It's often more to say like, we developed this cool feature for our whatever it is, and we're going to explain it to you with this little prototype, which is often in the form of like a Jupyter notebook or a blog post or something like that. And then we have to keep updating and maintaining these prototypes over the long term and including new features in them as we launch new things that integrate with whatever the feature was we launched. So for example, if we add a feature like a new way to measure something, and then later we add a way to track how many tasks you're running, then we have to update all of the prototypes to include the cost tracking. And this is just a different model from the way a lot of academic prototyping works. I don't mean to say that it's better or worse, it's just different, which is fine. You know, it's a big world out there. And the target user for these prototypes is usually not a scientist or trainee with domain expertise. So the person we often have in mind here is either, you know, like they're a software developer who doesn't know anything about our domain, or they may be somebody who knows a little bit, but they're not ready to be like an expert or a developer who is like actively contributing to the code. Or on the other hand, they may be somebody, again, coming from academia who is a domain expert, but doesn't know how to integrate with our tool set at all. We often, you know, you'll often see like if somebody is trying to come to a new, like they're trying to start a project on, let's say, some conglomerate's software tool set, there's a whole lot for them to learn that they just aren't exposed to because it's different tooling than they use day to day. And so we have to find a way to communicate to that to them without writing a full novel. And then, as I mentioned, we often develop these internally to make the case for a new project and to give software engineers we work with something to build off of. So we usually don't own the end-to-end, like I built a prototype and then I translated it to run on HPC and then I wrote a bunch of test process. We contribute to that in a lot of ways, but it involves, I think, a lot more collaboration with folks with maybe more of a CS background than many of us would be used to in academia. And when we're developing industrial software libraries, we also have, I think, more sort of considerations for how this interacts with external customers and users, especially because changing any public interface is a really big decision if somebody is paying you a bunch of money to work with your interface. You may break things for external users who are dependent on that, on whatever the interface was. If you introduce something new, it can be hard to walk it back because people will start using it and become dependent on it. So you have to really be sure you like the change you're making before you go forward with it. And we're supporting a lot of different users, both people directly working with whatever it is we're doing, people from third-party plugin developers, and then other people inside like our team or other people in the company who are developing our stuff. Now, this probably isn't that foreign to folks who are working on big scientific software libraries in academia. But I think especially the third-party developer angle is a little bit different because often, again, just my experience, when folks are developing plugins for like iTensor or something, those users are far more willing to come to iTensor and be like, hey, this isn't working, versus they know somebody who's using a third-party software for like quantum computing that works with us doesn't necessarily know even who they should go complain to if something doesn't work. So we have to find a way to make sort of the joins comprehensible to them so they can get the help they need quickly. We also generally have a more defined coding style. So some folks have like a very specific Python style guide, for example, or Julia style guide that they have to use. This is to enforce consistency and make it easy for external, like people who are not on the team, reviewers, to look at our code. But it also means that if you have an idiosyncratic way of coding that you like, it can be frustrating because now you have to work with this defined style that maybe isn't your preference. So in general, you kind of have a less permissive environment to like really go off on your own and try stuff, which can have, again, good and bad sides. And we often also have sort of comprehensive documentation that includes like what we might call a manual. So this isn't even like tutorials or documentation that's in line with the code. It can be like a very sort of like a chapter book explaining what the software is, how to use it, what to like, when to use a feature or when not to use it, which is often, although not always, not a feature of academic libraries, partly because we assume with the domain expertise, like folks already know, for example, like what an energy functional is that they're trying to calculate. They don't need that explained to them. And they don't also need it to be explained like when they should or should not be calculating something like that. Another aspect I think that it's quite different is especially for software that third-party customers are using, we have this whole concept of getting paged. Has anybody here ever been paged? Yes, one or two people. So if you're not aware of what this is, if somebody reports that they're running something and it started to fail, or all of our build pipelines start failing, someone's phone makes a noise at like 80 decibels whenever that starts happening. And when I say whenever, I mean whenever. Like it could be 3:15 a.m. in their apartment and they're getting woken up and they have to deal with this. So if you committed code that caused that to happen, they won't necessarily be angry with you, but they would like to prevent it from happening again. And so we always have to think about, like, when we're making changes to this code, what is the risk of somebody, is this going to up or lower the number of people getting paged and how frequently that happens? What can we do to minimize the amount of paging that occurs? And how can we, is there a way we can change the way our software runs or the build process? Can we strip out dependencies to make the chance of this happening lower? And again, it's just something that in an academic environment, because usually, academics are not getting woken up at 3 a.m. for this, we just don't have to worry about, because nobody is coming to us being like, hi, like I was woken up at 3 a.m. because of your code. Can you please fix this? So it's another example where there's an incentive for us that just doesn't exist in another environment. And maybe for academics, that's good. I mean, it's not great to think you woke somebody up at 3 a.m. Or 2 a.m. That's also not a good time to be woken up. But this is just a sort of another way to think about like the different considerations you have to worry about when you're working in these two different paradigms. And I know, like, at least when I was at Flatiron, we had a lot of discussion about sort of the right way to do testing. And this is another angle where there's sort of a wider sphere of things we're worrying about, but there's a lot of commonality as well. So of course, we do a lot of unit testing. Probably many of us here are familiar with this, where you're testing functionality of the individual pieces of the code. You may be mocking something if they're calling some external endpoint, like, if they're making some HTTP request to something, you may mock that or something like that. Then we have integration testing. So this could be testing, for example, if I run my entire workflow for like my protein folding or whatever, I want to make sure that that in the end returns the correct answer. And if it interacts with other libraries, that shouldn't break. It should both return the correct answer and not break, especially if I support multiple versions of another library. It should be correct for all of them. And then there's angles that were completely new to me when I started working in a more industrial environment. Canary testing, which is kind of similar to A/B testing, if you heard of that. In this model, you release some new change to a really small fraction of users, and then see if something breaks for them before just letting it go crazy in the whole wide world. This gives you a chance to avoid breaking everybody's use case. And then smoke testing is another example. This is when you run like a very sort of restricted subset of the unit and integration tests almost every day, sometimes multiple times per day. These are the things that absolutely cannot break, and this protects you from wasting a lot of resources running tests too frequently, and it also protects you from breaking something really important without realizing. And then another aspect that I mentioned earlier that we have to worry about that I think is maybe a little foreign coming from an academic environment is dealing with security. So I've chosen this picture. This is a star fortress in France. You can see if you're living in the town here, you would have really good visibility to anything threatening happening near you. And this also has a bunch of layers to protect you from, anything bad headed your way. And so this is kind of maybe a mental model for what we're trying to do. We're trying to keep the various things we know people want to do that maybe aren't so great in sight, and we want to have a kind of a series of layers that will protect us and our users from doing something that they didn't intend. So for example, if we're integrating with a dependency that has a specific open source license, we have to check that we're complying with that license, because if we're distributing that code, we probably have to give attribution to the code authors, or even more more terms can apply to how we deal with open source code that's governed by particular licenses. And of course, this is something where if we don't comply, legal is not going to be, they're also going to get woken up at 3 a.m. They don't want that. And we also have to worry about responding to security alerts. So for example, a dependency we integrate with may have a security alert. Like for example, if a SSL library has some security vulnerability, everybody on our team might get woken up to deal with this, to make sure we patch everything, deal with it, versus just telling people like, it's fine, just update. And it's, again, just a different model, like where the responsibility is and how we can make sure to avoid breaking stuff for other users. Another aspect that I think is quite different from academia is often if we're releasing code to the public, we'll have a review from a security team. So these folks are not necessarily domain experts. In our area, they're domain experts in security. And so they'll look at our code and say like, this is a security vulnerability for these reasons, you need to fix it. And then we say, well, that totally breaks our design. Okay, too bad. I mean, you can't release code that's going to allow users to have their account hijacked. It's simply not going to work. And some of our code that gets released will have like penetration testing, or what's called red teaming, where the security engineers try and take the role of like, the villain, I guess, and then try and break stuff for us to make sure that we've done what we can do to protect users, which is something that, at least again in my academic experience, was not an angle, and it's just something that we're usually, coming from academia, we're not used to worrying about, right? Like, am I leaking someone's SSH credentials? Am I revealing an access key that I shouldn't? Things like that. And then we also have stuff, automated reporting from our computing resources. And in general, we're always worrying about like, how could somebody use our code to do something nefarious, and how can we protect users from doing something they didn't intend to do? So despite not having as many slides as I thought, I am gonna have to go through this last one relatively quickly. So I think I just want to sum up that we kind of have different tool sets and mindsets, just because we're responding to different environments, different incentives. So I'll just quickly ask again, who here has written a YAML to do GitHub Actions? Quite a few. And how about written and distributed a Docker container? Also a few. And if anyone's had to do this with like a non-public GitHub repo, do you know how to do that without leaking SSH credentials to the wider world? Like one or two? Yes. So this is a problem we often encounter, where we need security to come and be like, all right, do not leak your SSH private key, please, when you distribute Docker code for everybody in the whole wide world to use. And we also have to worry more about providing services to users who aren't English speakers, and supporting the various accessibility needs that folks have. For example, supporting users who are blind or visually impaired, and handling things like security testing. So in the interest of giving people a chance to ask questions, I'll just stop on this slide and not read it for you. Thanks for your attention. And yeah, if you have any questions. Water.
Okay, thanks. That was great. My main takeaway is that we need to implement paging at Flatiron.
That's your words, not mine.
So yeah, we have time for a couple of questions. How about Dan?
So you've seen the academic side and the industry side, and this is maybe a loaded question, but which do you prefer?
Oh, it is a loaded question. It's a good one too. I think it really depends which day of the week you ask me, because sometimes I get really frustrated because I'm like, why can't we just merge my code? It worked on my machine. It's fine. It's good. Like, once these guys see this, they'll love it. But then other days, especially if I have to work with someone else's code, I'm like, dang, these restrictions are great because I can guarantee that, this person's software that they wrote 3 years ago, this person is no longer on the team, will still run on my machine and I can build on top of it. So I think it really depends. Like, as I was saying, there's kind of advantages to both, and I don't think one is right or wrong. There's maybe more permissiveness in the academic environment, but that also leads perhaps to more risks where you can run into code that's not supported or security issues or stuff like that. So yeah, you should ask me on Monday. And then
maybe one more. Yep.
Question about testing. So one challenge we have with Rosetta and so forth is a lot of our methods are stochastic, and you might run a test with one random seed and get a positive result, and then run it with another one and it fails. In the future, this is going to be a fundamental problem with quantum computing. And you said you work on bracket. There's no such thing as a fixed random seed in quantum computing. How are you planning to deal with that?
Yeah, so I mean, for the software testing angle, then this is also, of course, something that folks in HPC think about a lot too, right? Like, how can you seed many parallel random number generators in a reproducible way? So we use a lot of techniques from sort of that research for doing the software testing angle. And then for device testing, so if you have like a quantum device you want to test, we work a lot on thinking about, yeah, like what is like a statistical measure we can use to determine the correctness of the device? What is a reasonable thing for the device to do? And how can we distinguish that from an unreasonable thing? And that's also like tied into a lot of the fundamental science we do of like, in a quantum computer, you have a noise model, right? What are the errors? So how can we verify that the device is working properly if we don't even know what the noise model is? And how can we verify our noise model then? So there's a lot of research, especially for quantum computing, going on right now of like, how can you verify and test that the device is doing what you expect? And then how can you also test that your model of how it's going wrong is right? I guess the short answer is model of how it's going wrong is right. I guess the short answer is it's complicated. And I don't want to take up too much of your time. So do we have time for one more?
Maybe we leave it at that. And if you're sticking around, people can ask questions. Yeah. So thanks again, Katie.
Thank you.